So here's a review of all of organic, including diploma questions. I like to do this review at the end of the unit before the unit test or as a review before the diploma. So just going over everything we've done already. To start with identifying organic compounds. So we know that it's a compound that will contain carbon. We also know that there are some exceptions. So like carbonates, arcyanides, are carbides, oxides of carbon, so carbon monoxide, carbon dioxide, and if you have anything bonded to a metal, you're no longer organic, you're automatically inorganic. So I personally like these diploma questions that you're just identifying organic or inorganic compounds, because as long as you know those rules, these questions are nice and easy. So organic, metal, not organic, organic, it's an oxide, so not organic, CN, not organic, organic, it's a metal, so not organic. So this would have been 1, 3, 4, and 7. Another one that's very similar, just going through the same thing. We know we can rule out the ones that are inorganic and then write down the rest. So 1, 3, 4, and 6. From there, we started to take a look at organics reactions or compounds that you saw in everyday life. So here are common alkanes and hydrocarbons, that would be fuel. You look at, once again, the reaction for photosynthesis, because that has organic compounds in it, and cellular respiration can come up as well. So with this one, match the chemicals numbered above with the statement given. So the reactants in photosynthesis. So your reactants are going to be carbon dioxide and water that come together, and the products of complete hydrocarbon combustion in an open system. So combustion is always your hydrocarbon in the presence of oxygen, and you always produce carbon dioxide, so we'll write that down, and water. If you're in an open system, your water can escape, so it would be the gas state. Now, in terms of naming, we want to know how to name everything that's listed here. So alkanes, when you have single bonds, ends in A-N-E. Alkenes, ending in E-N-E. Alkynes, ending in Y-N-E. So that's when you have that double or triple bond. Knowing that difference, that alkanes are saturated because every carbon is bonded to the max number of atoms possible. Alkenes are not saturated because you're taking away the max bonds possible. Same thing with alkynes. You need to know that you can have cyclic, so rings, and if you see that, you have that word cyclo in there. You have benzene, and if you have benzene, you are an aromatic compound. If your benzene molecule is connected to a chain longer than 6, then benzene becomes a phenyl branch. You also need to know the halogenated hydrocarbons. So if you see any halogens and how we name them, alcohols with the OH and where we place them, carboxylic acids we need to know. The last one would say esters. Then knowing how the branches work, that they need to be named alphabetically. If you have more than one, you need a multiplier. And the difference between nonpolar and polar. So all of these here are nonpolar because we just have those carbons and hydrogens. As soon as we're adding on some of those atoms that have lone pairs, we're now getting into polar molecules depending on those functional groups. So looking at naming this cyclic hydrocarbon, going through it, the first thing we can do is rule out A and B, because if it's cyclic, you must see the word cyclo. Then you name alphabetically, and an ethyl group would go before a methyl group. So this would be D. Going through this, naming compound number 3. So there's many compounds, but if I name compound number 3, you want to number your carbons. I'm going to number from left to right to give my first branch on carbon 2. So this would be 2,3 dimethyl pentane. So 2,3 dimethyl pentane. A is a distractor if we numbered in the wrong direction. Okay. Now the other part is being able to look at a formula and knowing if your compound matches that formula and seeing the correct name. So going through this, I'll just start with that first one. We know that if it's benzene, you have alternating double bonds. So why I'm just drawing in very scribbly those double bonds is to know that at each of these carbons, you have a hydrogen. So now we can count it all. So from the first one, you have 1, 2 carbons. On the ring, you have 6, so that would be a total of 8. Then count your hydrogens. So 3, 4, 5, 6, 7, 8, 9, 10. So we don't have enough in that one. So now we can check the next one, and we're just going to keep going. So still has 8 carbons, 3, 4, 5. There would actually be 1 hydrogen there as well. But would there be 1, 2, 3? No, there wouldn't. Never mind. So over here, counting them, we have 3, 4, 5. There is 1 hydrogen here. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this one can work, but we need to check the name, and the name also works. So this looks like the answer. I like to look at the rest just to see and make sure I didn't make a mistake. So C I know is wrong because cyclo's written in the wrong spot. D, this is a propyl group. It is on cyclo, but it says pentene, and that means there should be a double bond in that ring, and there's not. So we can be confident our answer is B. Now, our next one, what is your molecular formula? So I tell my students that if you like formulas, you can memorize them, but if you don't, you can just draw it. So if I was to draw cyclohexane 1-ol, that means I have 6 carbons in my main chain. And if I numbered my carbons, 1, 2, 3, 4, 5, 6, on carbon 1 is my OH group. And then on carbon 2 and 5, I have methyl groups. So CH3, CH3. And then I know that at every spot, I'll have hydrogens still. So there would be 1 hydrogen right here. There would be 1 hydrogen right here, 1 hydrogen right here. There would be 2 hydrogens here, 2 on carbon 5 and 2 on carbon 6. So I know that's getting a bit messy, but let's count that now. So we have 6 carbons all together. So you can rule out this because 6 would be in the ring. And then we have 2 from the methyl groups. Then we have 1 oxygen. So far, C8O1, and now count your hydrogens. So 3, 4, 5, 6, 7, then 8, 9, 10, 11, 12, 13, 14, 15, 16. So it looks like our answer is D. So if you're ever unsure, just draw it out and count. Going through these questions, I also like these because, again, as long as you know what your compounds are, they're fairly easy. So one compound that's an alkene, you're just looking for any compound that ends in ENE. So this would be number 1. An alcohol needs to end in OH. So number 6. A triple bond must have YNE. So number 4. And then cyclic and saturated. Cyclic means there's a ring. So we're looking for one with cyclo. Saturated means it's all single bonds. So ANE. That would rule out number 1, and it would be number 5. So 1, 6, 4, 5. Keep going. If you have benzoic acid, you definitely would have a carboxyl group. And then over here, picking between aromatic and aliphatic, the only way to be aromatic is to have a benzene ring. And if you're benzoic acid, you do have benzene, right? Because that would be the benzene ring. This is one of those compounds you have to have memorized. So you'd have the benzene ring, and then you have that double bond O with that OH group. So because there's benzene, it is going to be aromatic. Over here, 2 properties that cyclopentanol and pentanoic acid have in common are they have the same number of. So I think the same thing. I would probably just draw this quickly and check. So if I have cyclopentanol, that means I have an OH group on my first carbon. If I have pentanoic acid, that means I have a 5 carbon chain. So 1, 2, 3, 4, 5. And my last carbon is double bonded to an oxygen that's single bonded to an OH group. So reading through this, I definitely can rule out B and D because there is no benzene ring. And looking at it, seeing what's similar, and this would be the carbon atoms in their parent chain, because in this parent chain you have 5 and in this parent chain you have 5. So we will pick C. We can also double check. It's definitely not the same amount of oxygen. This molecule up here only has 1 oxygen. This one has 2. So just another way to know that we are right. Looking at another one, both 2-methylpropane and 2-chloryl 2-methylpropane contain. So looking at this one, it says functional group or a branch on the second carbon in the parent chain. So in the first molecule, you have a methyl group. That is a branched group. In the second molecule, you have a hydrocarbon and a methyl. That is also a branched group on carbon 2. So definitely we have branches of methanol on each of those. And both have, if it's saying propane and propane, that would be 3 carbons in the main chain. So we've talked about this already, knowing the difference between saturated and unsaturated. So saturated has all single bonds, and unsaturated, you can have a double or a triple bond. So going through a few of these, this one actually is showing, the bromine test, and it's telling you we're adding a few drops of the bromine and seeing what happens. So I'm saying it's about the bromine test, but it's actually just referencing the bromine test with this box. But here, it's actually just showing we know the difference between saturated and unsaturated. So if you end in A and E, that's all single bonds, so it's either A or B. And if you end in E and E, you are unsaturated, so this must be B. Doing the same thing, again, it is looking like it's going to reference the bromine test, but it's, again, knowing the difference between. So heptane would be saturated, heptene would be unsaturated. So B once more. Okay, so we talked about this already within this video, but if you are aromatic, you must have a benzene ring. If you don't have a benzene ring, then you are aliphatic. So going through this, we have this compound here, and it's asking us to classify it. You have a benzene ring, so it's aromatic. And in terms of a functional group, this group here is a carboxylic acid. So this is D. It might look like there's an alcohol, but because that OH is on the carbon that's double bonded to the oxygen, you need to recognize that as a carboxyl group. Moving on from here, cyclohexane, E-N-E, and benzene have a different number of blank. That would be double bonds because benzene has 3 alternating, and cyclohexene means that you have a double bond between 1 and 2. So we'll cross that one out. And they are both alkanes. That would not be true. They are both cyclic because they're both rings. Going on from here, we have a carboxylic acid reacting, looks like with this complicated compound. Oh, it's talking about, I think it's talking about aspirin. And there's a little bit more information. So this is asking about the compound ASA. So we're looking at this one here and how it is classified. So, I need to read this properly. And we're asking about molecule 1. Molecule 1, and I think these can be a bit confusing with your diploma questions, but what's above 1 is this one here. So we're not looking at that one. This one here, if we were going to label it, it is not aromatic because it doesn't have a benzene ring. So it's either A or B. And then compound 2, being able to classify that, you do have a carboxylic acid group, but because you have this link in here where carbon is double bonded to an oxygen, single bonded to an oxygen, that's also bonded to a carbon, that's an ester link. So this is going to be A. Okay. So that is to start. Now we have all our functional groups. So if you have a halogen on your chain, that's a functional group. If you have an OH on your chain, the carboxylic acid, or this one here where it indicates a ester. Going through this, an ester functional group is found. So going and taking a look, we want that ester group or that ester link. So I'm seeing one here. So it's always carbon double bonded to an oxygen and bonded to another carbon. That same carbon that I'm looking at is also bonded to an oxygen that is bonded to another carbon. And this could be a carbon by itself with hydrogens or another chain. So your ester functional group, we've already identified 3. Looking at molecule 1, I don't believe this is 1. Looking at molecule 2, looks like we have that ester link right in here. And molecule 4 does not have 1. So it looks like it's 2 and 3 only. Doing similar, just looking at those molecules, something that's aromatic, you need a benzene ring. So here you could pick 1 or 2. So the diploma would accept either 1 or 2 for that one. So it would be a series of answers here. Carboxylic acid, we're looking for this link in here where carbon has an OH group on it. So this would be a 3. Unsaturated, so you're looking for an alkene or an alkyne, and aliphatic means no ring. So unsaturated, double bond, we're looking for not a ring, so this would be number 4. And a halogenated hydrocarbon, you should see halogens, which is like bromine here, so that's number 2. Okay. Another example, the organic compounds number above, that's an alkene, and an ENE is number 1. An alcohol is number 6, triple bond ending in YNE. Cyclic and saturated means a ring that has all single bonds, so number 5. Okay. So I think we'll pass this one because it's a lot of the same thing, but I hope you can see how these questions start to look a little repetitive. They're very, very similar. Same idea. Yeah, we can do this one. So butanoic acid can be described as, butanoic acid is this one here. It does not have a benzene in there, so it's not going to be aromatic. And the functional group, if it ends in oic, we know it's a carboxyl group, but also we see that COOH, so this will be A. This one up here, I do like this question because especially with the branched and unbranched can get a little bit confusing. So all of these, because you have methyl and ethyl groups, are going to have a branch. So going through this, what would apply to methyl cyclopentane? With questions like this, I do like to just draw it because I think it's easier to answer. So I would have a methyl group on a 5-carbon ring. So going through the structures that and descriptions that apply to this, we have number 2 matches it, not 1 because there's a benzene ring, not 3 because there's too many carbons, and we have the wrong side group on the chain. It's definitely branched because you have the methyl group. It is unsaturated because it ends in, it's saturated because it ends in ANE, and you have all single bonds. And this, because it again ends in ANE, that's classified as an alkane. So this is one more term. I've had another video that we do talk about it, but it's one of those things that you know it or you don't. So to be an isomer, you break down to the same chemical formula. So you'll have the exact same number of every atom. They are just arranged differently and react differently. So they have different names. So an example, if you had pentane or 2-methylbutane, they both would have the molecular formula C5H12. They react very differently. They're different molecules. They look different, but they do have this in common. So going through a question that implies, isomers, it's asking which one of these 7 molecules is an isomer of this first molecule. So for this first one, we want to recognize how many carbons you have, which you have 4 in the ring, and then 1 from the methyl group and 3 from the propyl group. So that would be C8. And then for hydrogens, it's easy to see the ones on the branch, but from the ring, you would have 1 beside the methyl group. You had 2 over here. You would have 2 down here, and you would have 1 more here. So then that's just that reminder that every carbon can bond to 4 atoms. So if you have 2 lines or 3 lines, you can figure out how many hydrogens you can add in. So counting those, we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're looking for isomers of C8H16. So let's go through that. Number 1, 1, 2, 3, 4, 5, 6, 7, 8. Could work. Count those hydrogens. There would be 8 on top, 8 on the bottom, which would be 16, 17, 18. So that's too many. Oct3ene, again, we can draw this quickly. So 1, 2, 3, 4, 5, 6, 7, 8. On carbon 3, so between 3 and 4, you have a double bond. So that fits 8 carbons, but now you have to just double check your hydrogens. So you'd have 3 here, 2 here, 1, 1, 2, 2, 2, and 3. So counting those, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So number 2 is the first isomer. And then we just keep going. So let's keep looking and going through this. And I just draw all of them out. 1, 2, 3, 4, 5, 6. And then dimethyl. So we'd have 1 here and 1 here. And you have a double bond between 2 and 3. So now if I filled in my hydrogens, 3 here, none there, 3 here, none here, 3 here, 2, 2, and 3. So counting those, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Looks like number 3 will work. I'm just going to keep going here. 3, 3, dimethylhexane. 2, 3, 4, 5, 6. We have 2 here. So counting all of them, hexane, 6, 7, 8. Carbons work out. Count those hydrogens. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So not enough. So it's not going to be number 4. Number 5, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. Then count your hydrogens. 3, 4, 5, 1 here, makes 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So number 5 is, and then looking between the last 2, it's either going to be 6 or 7, but going through it, I'm just going to look at 7 first because it looks a little bit easier to deal with. So I need those alternating double bonds. 6, 7, 8, I have enough carbons. Double check your hydrogens. So 6 from the outside, none here. 6, 7, 8, oh sorry, not 8, it would be 1. 7, 8, 9, and 10. So not enough. So the last one that should work out should be 6. Now, same idea. If we were able to do the last question, you could do this question. Asking for isomers, you're just seeing what can be the same formula. So you just go through. So if I just look at number 2, because I think it's an easier one to look at, I would say this has 1, 2, 3, 4, 5, 6 carbons. So I'm looking for C6. And then counting my hydrogens, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. H14. If any of the other compounds can be C6H14, they would be isomers of each other. If there's no other compound with C6H14, then it does not have an isomer. Okay, going through this, same idea. I would suggest drawing these all out and checking what would match. Okay. So moving on to some physical properties, you do want to make sure you're studying the physical properties as well. So when you're looking in general for boiling point, it gets bigger or larger when you have longer chains. Because you have more LDF forces, meaning more electrons, you need more energy to break them apart. When you're looking at polarity, if you have just carbon and hydrogen, we're not polar. As soon as you have any oxygen or a halogen, you are now a polar molecule. We do know, and we should remember, that like dissolves like. So if you're non-polar, you are not going to dissolve in water. If you're polar, you will. And if you do have a polar molecule and your chain becomes really large, like this example where you have an OH group on octane, so 8 carbons, your molecule gets less polar because that OH group is getting less significant. Okay. So moving on from here, and this is now understanding boiling points, comparing it. So we have the information about all alcohols. So we have 3 different ones with 3 different boiling points. It says that they have the same blank. They wouldn't have the same structural formula. And you can tell because right away we have different carbons that the OH group is on. So for lack of time and figuring out how many carbons and hydrogens we have in O's, oxygens, it's definitely going to be molecular. But they will react differently. And so we have different chemical and physical properties. So for this one, I'm going to go with A because of the reactions. If it's really emphasizing on the boiling point, we could also say physical. Now, this next one, being able to list from lowest to highest. So here we have all carboxylic acids. The lower boiling points will be the molecules that are easier to break apart. So lowest boiling point, I would think, would be your smallest molecule, which would be methanoic acid. And then your boiling point gets larger as your molecule gets larger. So then 1, then 3, and then 4. Right. Okay, going through the next one, we have, we have our reaction, you have a catalyst. Here is now showing that we know some of these organic reactions, and if you are breaking a double bond, it is an addition reaction. So we can rule out substitution. And then same propa 2 all, because you have an alcohol, you are polar, and polar is soluble in water because water is polar and like dissolves like. So this would be C. Okay. So this was just going over it, but going over it one more time. If you have an addition reaction, you do have an unsaturated molecule because you're breaking a double bond. Elimination, you have a saturated molecule and you're forming a double bond. Esterification is always that carboxylic acid coming together with an alcohol to form that ester, and water leaves the molecule. So this is also known as condensation. And you have substitution, where you have 2 molecules and something will swap places and you get 2 new molecules. You also have combustion. I like that there's this note here not emphasized in organic. You will still see it, so still know it, even though it might not come up as much in this unit, it will come up in the other units. Okay, so this one, during an organic reaction, if unsaturated, so unsaturated means you have a double bond, becomes saturated means you have a single bond, so that would be double bond breaking. If you break a double bond, you are adding to the molecule, so that's an addition reaction. If you have pentene coming together with hydrogen gas and it's undergoing an addition reaction, the resulting product would be, so going through that, if you have pentene, that would be carbons, 5 of them in a row. You have a double bond. It's not saying where, so you can put it anywhere you want. And then you have all of your hydrogens. So if it's telling you that you are undergoing an addition reaction, that means one of the double bonds will break and each of your carbons, actually now I should be putting that line, can bond to one more atom. Those atoms will be hydrogen. So our remaining result, our product, will be an alkane. So we can just go through it. It's not halogenated because you didn't add a halogen. It's not going to contain a double bond because it's broken. And it's not going to make a bond. So the only answer could be C. Okay. Moving on to 24, asking which of these molecules, if reacted with bromine, would lose its color. So this is referencing that bromine test, and that bromine test means if you're losing its color, you are in addition reaction, so you're breaking a double bond. So we're looking for all the reactants that have a double bond to be broken. So it looks like our answer is 1, 4, 5, and 6. Okay. This esterification reaction is showing we understand an ester. The part of the ester that's bonded to the oxygen came from the alcohol. This has 2 carbons, so that would be ethanol. And then the part that's double bonded came from the carboxylic acid. So that's 5 carbons. So that would be pentanoic acid. So this has to be D. Keeping with our reactions, the reactants that undergo blank reaction and the products would be 1,2-dibromo. So this C2H4 looks like this with all your hydrogens. If you add in bromine, that means this double bond is going to break and each of these carbons will take a bromine. This type of reaction is addition because you're adding to the reactants, and your product, because the double bond broke, is ethane. So that would be C. Okay. Showing more of the reaction. So we have a type of reaction. So the first part, we want to recognize that this is esterification. So starting with, you have a carboxylic acid, right? We see that with that group. We have an alcohol, and you form the ester. So your ester link is right there. So this is 8. Name of compound 1, 2 carbons. It's a carboxylic acid. This would be ethanoic acid. Name of compound 2. So you name your alcohol part first, 2 carbons. So that would be ethyl, and then ethanoate, so that would be 3. And then classification of compound 2, that is an ester. Okay. Our next one, you have polyvinyl chloride, which is a type of polymer that you use to make pipes and siding. The polymer is vinyl chloride, and it's showing how it's produced. So then the reaction in equation 1 is an addition reaction. So we hopefully can see that right away. And the product is here, it's not just an alkene because we don't have a double bond. Could be an alkane, but you do have that halide being added to the molecule. So the best answer is going to be B. Okay. The last thing we cover in Chem 30's organic unit is polymers. And that's when you have a long continuous chain of monomers. Naming them is relatively easy. You just add poly in front of the name. Now, there are 2 different ways you can make a polymer. One is your addition reaction, where you break double bonds and link everything together. The other is a condensation reaction, where oxygen is usually the link in a ester bond, but sometimes you can have an amide bond, and that's when you have a nitrogen present, but it looks similar and it does the same. So here, looking at this one, we have ethene added to ethene, and we see that we're making a polymer. So ethene, even though it's looking like a polymer reaction, it's not asking you that. It's just saying what you can classify it as. It's not aromatic because there's no benzene. It is not saturated because you have a double bond, and there's no halogen, so the answer has to be C. Now we can start to look at how you convert ethene into polyethene. So starting off with, ethene would be the monomer because that's what you're linking, and to make it, you have a series of addition reactions, and if it's not saying addition, you're just going to call it polymerization. We know it's not esterification because you're not forming an ester. Okay, number 27 of this old diploma question, which of the rows identify the reactant and its product in polymerization? So if you have ethene, it's going to turn into polyethene. So it cannot be the first one. It could be ethene. It could be the second one. It's definitely not the third one. Then you have propene turning into polyethene. Can't be that one. If it was propene, it has to be polypropene. Now, one of the last things that come up quite often is fractional distillation, but you could also see cracking and reforming here. So with this, I usually just get the kids to read it over in their textbook, but to know fractional distillation, because that one comes up the most. So if you have a mixture of hydrocarbons, like here we have a mixture of methanol and ethanol, you can separate that always by fractional distillation, and that's always separated by boiling points. So that reminder is if you have that distillator and a bunch of hydrocarbons in there and you heat it up, so you add in heat, those smaller molecules will escape first and there'd be openings here and you can collect it. And then as the molecules get bigger, it has different boiling points. So it takes longer to separate and turn into a gas, but eventually you can collect it. So it's always based on boiling points. And then here is that old diploma question that this picture comes up lots, and this is exactly what's mentioning. So this was that crude oil mixture of hydrocarbons. Those smaller carbons will come out first. The larger hydrocarbons will come out last. And so that would be fractional distillation. And in this case, your answer was D. So I hope that was a good review for you for organic chemistry. If you found this helpful, please subscribe. And if there's any other video I can do, please let me know. Thanks for watching.